So in this video we will be talking about an interesting property of Eisenstein polynomial and how they help us to find ramified primes, or more generally totally ramified primes. So to begin with, an Eisenstein polynomial is like a monic polynomial. Let's say something like this, where I'm taking all my coefficients to be, let's say, from integer, and this is Eisenstein at a prime p if p divides all these coefficients um, and p square doesn't divide the constant. So it's like the constant term should be p times some other number which is coprime to p. So such a polynomial is called Eisenstein at a prime p. For example, this polynomial is Eisenstein at 2. Right. So all right. So what and the second thing, so there are two words, right? As I said in the beginning, one was Eisenstein polynomial and another was totally ramified prime. So what's a totally ramified prime? So let's say you have some extension, some finite field extension of the Q, rash field of rational numbers, right? And say L over Q is a finite extension. So if you start with any prime number from Z, and so the ring of integer here is Z, and here it is, I'm calling it to be OL. So if you take any prime number P, any prime P, and you look at the ideal generated by P, not inside Z but inside OL, write it like this. Now we know that ring of integers of a number field, so L is called a number field when it's a finite extension of Q. So it's a Dedekind domain more generally. That means that every ideal can be written as product of prime ideals. For example, Z is a Dedekind domain because there is this unique factorization theorem, right? That every number can be written as product of primes. So here there will be some primes. So this pi is a distinct prime. Suppose there are many of them, and each pi repeats ei many times. Okay, so this p is called ramified if some ei is at least 2. That means it's not a product of all distinct primes. One of the pi has to repeat twice, and it's called totally ramified if some ei is equal to the degree of the extension. And in this case, clearly, say p1 repeats as much as the number of as much as the degree of this extension. Should be q. Then p1 is the only prime that will occur in this expression, right? Because so it's a result that you have summation ei fi 1 to r is the degree of the extension, where fi is this. The residue field extension, the degree of the residue field extension. So you see, if one of the ei is the degree of the extension, then r has to be 1, because the right hand side is exactly the degree of the extension itself. So in that case, r will be 1, and clearly f1, there is no f2 and beyond, so and f1 has to be 1 as well. So in that case, the prime will look like, say, p1 power n, where if I call this thing to be n. So there is a single prime lying above the little p. So for example, the easiest example is the number 2 inside, so 2 is ideal generated by 2 inside this Gaussian integer. So this is the ring of integer of qi, and you say 2, the ideal generated by 2 is same as this. So here the degree of extension is 2, as well as the power is 2, this number. So it's a totally ramified. Extension. Alright. So that's what a totally ramified prime is. And okay, so let's now come to the main result, and there are two parts to this result, so let me write it in two separate theorem. So the first is, so let k be k adjoint alpha, where alpha is a root of a polynomial that's is Eisenstein at some prime, at say prime p, then p is totally ramified in k, and the other way, the next theorem is basically says the converse, means let k be a number field and prime p is totally ramified in k, totally ramified in k, then k is generated by some alpha, which is a root of Eisenstein at that p. Right. So this is basically the other way of theorem 1. And surprisingly, both the proofs are kind of easy. So if I start with the first proof, so let's see the first one. So the first one says that you have given a root of an Eisenstein polynomial at some prime, right? So then how do you proceed? So let's start with the polynomial. So this is the proof of theorem 1. So you write the polynomial, let's write it as this. Where P divides each Ci, but P square doesn't divide C naught. That's the definition of Eisenstein at prime P. So, and alpha is the root of this equation, right? So when you put alpha to this equation, you basically get 0. But when you do mod P, what will it be? So, okay, so for now, let's suppose this is P to the E times some ideal A where A is co-prime to P. Okay, so we basically have to show that E is n, right? Where n is the degree of the extension. So this is we have to show. So we show E is n. That means it's enough to show that E is bigger than equal to n, because n is because E is anyway lesser than equal to n. We just have to show the other way inequality. So then if you look at this equation modulo P, because all the other coefficients are divisible by P, you basically only get the leading term, which is the alpha power n, and there is of course 0 because f of alpha is 0. So this mod this. Alright, now P is a prime number, P is a prime ideal. So if P divides alpha to the n, then P also have to divide alpha. That means we have this. Okay. And now all the other Ci are divisible by P, right? So that means what? P is this. When you view these things inside OK rather than the integer. So that means you get P to the E, the script P, mathfrak P to the E divides Ci for all I. Right? So that means you can just write this thing as Ci alpha power I is congruent to 0 mod mathfrak P power E plus 1, right? Because each Ci is divisible by P to the E, and also alpha is divisible by P. So as a total, there is at least one factor coming from this alpha power I for whatever I it is, because I is at least 1. And Ci is always divisible by P to the E. So as a whole, for each I, this is divisible by P to the E plus 1 at least. Right. So that means what? That means when you just look at this equation, so when you put alpha in this equation, you get alpha to the n, right? And there is this intermediate term plus C naught, this. Now this is then divisible by, so this is congruent to alpha to the n plus C naught, which is congruent to this, because all these terms are divisible by P to the E plus 1, and the right side is anyway 0. So you get, when you view this mod P to the E plus 1, you only get this. Okay. But now you notice that the C is divisible by small p exactly once, right? Because there is no higher powers of p in factorization of C naught. So that means, and also this ideal, in this factorization, the mathfrak p appears exactly e times, because the rest of the factors are, there is no p in the rest of the factor, right? We have already extracted out all the possible powers of p that is there. So that means when you look at this ideal, the generated by C naught inside OK, what you're gonna get is that this is divisible by p to the e, but not by higher power, right? Just from this equation only. Okay. So uh, how do you prove it formally? It's just a simple thing, because you look at uh, C naught inside this. This ideal you can break it into, let's say C naught is P times Q, where P is not divisible. P doesn't divide Q, right? Because C naught is divisible by P exactly once. So this is P okay, Q okay, and P is P to the E A, B okay, right? That means P to the E, uh, P to the E divides this. So this is the first part, which is easy. And now you look at, if P to the E plus 1 divides, that means what will happen, that P will divide B okay, right? Because there is P to the E coming from this factor, so you can cancel it out, the E many P, so you will be left with 1 P on the left. So P divides B okay. That means B, which of course belongs to this, is also inside this, right? Because then B okay will be P times some P dash. So in particular this is inside P. So B belongs to P. So that means B is here, which is just P okay. I mean, which is just ideal generated by P inside Z. But that's not possible, right? Because this will imply that P divides B, which is contradiction, because there's no P factor in Q. Sorry, this should be Q. Yeah. All right. So this is a contradiction. So this is the main thing that we needed, and now the proof becomes almost obvious, because so you have P to the E that divides, and this is the highest power of P that can divide the C naught, the principal ideal generated by C naught. So that means now you look at this equation, you combine these two equations basically. So you have C naught, which is divisible by P to the E, and what you had to prove is E is at least n, right? So P to the E divides C naught. That means you can write from this equation, let's call it star, and you have this star, double star. So that means what you can say is, now alpha is divisible by P, right? That is, we did it very before. So that means if you view this equation, so P to the N divides alpha to the N. We have this. So let's write alpha to the N plus C naught as P to the E plus 1 times P dash. You can write this from star. Okay, so this is from star. Okay. Now C naught is exactly divisible by P to the E. So you can factor out P to the E from both sides. So you will be left with this. Okay, so this doesn't exactly make sense, but you know what I mean, because then because from this star, okay, so let me be more precise. So from star, okay, you can write it as P to the E times some Q, where it doesn't divide. So you can just cancel out P to the E. So you get that now there is at least n number of p's that occurs here. So if I further write, because p divides alpha, so you can write this is as p double prime. So this is p to the n p to the e q e plus 1 p prime. Now you notice one thing, this q is not divisible by p, so there is exactly e many p's here, but there is n many p's here, and there is e plus 1 many p's here. So if e is smaller than n, what will happen? You can cancel out e many p's from both the sides, so you'll be left with this, which is the positive thing, q, and there is p dash. But now see, this is divisible by p, this is divisible by p, this will force that this, but this is not possible. So e has to be bigger than equal to n, that means e has to be equal to n. That is what we have to prove, right? So p is totally ramified. This is the one side of the proof. So it's just manipulation, this is nothing much. Alright, and now let's look at the other part of the proof. What does the other part tell? You start with a ramified prime in this case, which is p here. So you can just write it as POK is this. It is given, and you have to come up with an alpha which generates k over q, and which is a root of some Eisenstein polynomial at that prime p. So you have to come up with number alpha. So what will we do is, you take any alpha which is in p but not in p square. Okay, so that means alpha, when you look at the ideal generated by alpha inside OK, this is just p times some q, where p doesn't divide q. So alpha is divisible by p exactly once. Okay, and so what will you show is, you start with this alpha, so we'll show the following, that the characteristic polynomial over q of alpha over q is monic, irreducible, or say is monic of degree n over this in ZT, is Eisenstein at P. Okay. And we know Eisenstein polynomials are always irreducible. This is a any like first course in ring theory proves this. The Eisenstein polynomial is irreducible. So that will mean that this will also the minimal polynomial, and hence K will be generated. K will be. This will tell you that is minimal polynomial, and this will tell you that K is actually Q alpha, which will be done. So you just have to show that the characteristic polynomial of this is just Eisenstein at P. So for that we just start with so let's take some polynomial which is supposed to be the characteristic. So suppose characteristic polynomial of alpha over q is t to the n a n minus 1 t to the n minus 1 a1t plus a naught, where all these are integer. Okay, now we know that, so this is ft. So alright, we have to show firstly that p divides this, secondly p square does not divide the a0 term. Okay, now we have this, right? So what we can do, we can take the ideal norm on both sides. So for an ideal I, the ideal norm is just the quotient, the cardinality of this quotient ring. So from this 1, so from 1, when you take the ideal norm on both sides, you will get that the norm of this ideal, and whenever you have principal ideal, the norm of the principal ideal is the norm of the generator. So the left hand side becomes norm of k over q alpha. Of course the cardinality norm is positive, is p times q, norm of p times norm of q, p times norm of q. But now p is totally ramified. So in this equation, if you take norm, let's call it 2. So in 2, when you take norm, the right hand side will be this, the left hand side will be norm of p. But p is coming from the base field, so the norm has to be p to the n, right? P power n. So that means this is p. So this you put, this is this. Okay. And from the minimal polynomial, or from the characteristic polynomial of alpha, the norm is what? This is the negative 1 power n times this, right? So now you compare both of them. This will give you that clearly p divides a naught, right? Because plus minus a naught is p times something, so p has to divide a naught. So this is the one. So one of the coefficient, the constant term is divisible by p. We have to show that it is not divisible by p square, and all the other terms are also divisible by p. These are the only two things. So alright, but then if p square divides a naught, what will happen? If p square divides a naught, that means p will divide n of q, right? Because there is one p here, and so it will cancel out, but the remaining p will divide the remaining factor here, norm of q. That means p is a prime that divides norm of q. That means there's a prime that lies under the prime ideal that divides q, which means, but we know that p doesn't divide a, right? Where is it? I'm sorry, I mean p doesn't divide q. Yeah. So when you take the norm, there should not be any p factor, right? So norm of q cannot be divisible by p, because the ideal is not divisible by the only prime that lies above little p. Remember, p was totally ramified, so script p was the only prime that lies above little p. So this is not possible, and hence we get that p square does not divide it. So this is the easy one. Now the other one, so we just have to show that all the starting from a1 to an minus 1, all of them are divisible by p. Okay. So what we do is we do some kind of like an induction step. So if n is 1, there is nothing to prove, right? Because just k is q and done. So let's start with at least 2. So let's assume, just like the induction kind of stuff. So assume a1 to a n minus, or say a naught, we already did a naught to a n minus 1 are divisible by p, and we have to show that ai is divisible by p, just like induction. Okay, so you have this equation. You have this equation. You reduce this equation mod p. That means you reduce all the coefficients. So what will happen is only the first, these many terms will remain, right? Because all the other terms by assumption is divisible by p, so they will be gone. So it will look like this, and then okay, now you already have alpha is p times q, right? That was somewhere right, that was equation 1. So from 1, alpha okay is p times q. So now alpha to the n okay will then be p to the n times q to the n, but then p to the n is just ideal generated by p times q to the n, right? This is just raising this equation power n. So in particular alpha to the n belongs to p, okay. Okay, so then this belongs to p, okay. So you can further remove this term, and in fact what you can do is you multiply this entire equation by, let's say, so you can remove this term also, because this is divisible by this. Okay. Now what you do is so these powers of alpha runs from I to n minus 1, right? So somehow, so okay, so alpha to the n is in p, okay. So that means alpha to the n plus 1 and so on, all of them remains in p, okay. So somehow if you can make these terms bigger than n, then all of them will be inside p, okay, right? So that means if we multiply this equation with some power of alpha suitable enough, such that all the parts of alpha regard that they are with the a n minus 1, then say a n minus 2 up to a I plus 1. So you can, let's write this equation like this. So this is 1 I. So when you, let's say, just multiply with this, what will you get? See, this is the exact part that you need. You get the first term will be a n minus 1 alpha to the what will be, let's say, so this should be n minus 1 minus I. So this will be what will it be? This will just be, I think, what will it be? This is just 2 n minus 2 minus I. Next term will be 2n minus 3 minus I. This will be n, and this will be n minus 1. Now you see, except this term, all the numbers are bigger than n. This is n, this is also bigger than n, this is also bigger than n, because I is running from, remember, 0 to n minus 1, because I were the coefficients at this ai. So all of these are bigger than n, so all of these terms will be divisible by p. So the upshot is this is also divisible by p, right? And now this is easy, you just take norm on both sides, you get, so if I write, so let this is p times x, so you take norm on both sides, you get ai to the n, because ai is basically integer, you get norm of alpha power n minus 1, you get norm of p, which is just p to the n, and you get norm of x. Okay, and now what was norm of alpha? It was, remember, minus 1 to the n a naught. This is p to the n, this is this, but already we have that p divides a naught. So there is, and in fact p square does not divide a naught. So a naught is p times q, where p doesn't divide q. So you can write this equation. This is just obvious. This is this to the p q to the n minus 1 p to the n times something. You cancel out. There is n minus 1. There is exactly n minus 1 number of p in this expression. So you cancel out them. This, there is the p here and x. Now this is done, right? Because this is just a sign, and p doesn't divide q, so p divides the right hand side, hence p divides ai power n, and then that means p divides a, since p is, this is the, this we did it for I, and this is the induction, so this will prove as the other part. So you see, both the parts are kind of easy, proof of both the parts. So yeah, that's about this.